All right, folks, we're going to cover chapter 3. When is the exam again? Tuesday, because everybody voted and wanted it next week. So what we'll end up doing is check and make sure I got everything moved, okay? You should see next Tuesday is the exam. What we're going to do is we're going to cover the next chapter on Thursday so that you can do that. We did it in class. Yeah. So the exam has been moved. It now is reflected in the deal. You guys all forgot to remind me. Yeah. So I teach like solid blocks after these classes all the time. Typically like 4 hours of lab usually. And so I just do not remember anything after this. Yeah. So if you don't remind me, it doesn't get done. Okay. So the exam is going to be Tuesday. It's still over the exact same chapters. If you don't remember what those chapters are, you can just go on the dynamic schedule and it has it right behind it. Okay? No. Nope. No inner B, no chapter 4, just 1 through 3 and IA. Okay? Okay. So let's go to where we are now. All right. So according to valence bond theory, which is what we're starting to touch on right here, the carbon and methane would only form 2 bonds, and they'd have bond angles of 90 degrees. So if we were to make bonds with methane with the current understanding of orbitals that we have, then it could never make a tetrahedral shape, could it? There'd be no way to do that. It has s orbitals and p orbitals, doesn't it? And you really wouldn't be able to get to the s orbital because it's like in the middle of all the p orbitals, right? They're all jutting out there further away. So you'd be able to make 3 bonds. That's it. You're done. And they'd all have 90-degree angles. That doesn't sound like the current methane we know, right? So there's something else going on. The carbon in CH4, of course, makes a tetrahedral shape. This has a bond angle of 109.5 degrees. So how do we account for this? Well, we have to do something called hybrid atomic orbitals, okay? And so what we do is we take carbon. Carbon is going to have its orbitals mix. So one of the s orbitals is going to mix with 3 of the p orbitals. And you literally get something out that has character of 1 s orbital and 3 p orbitals. When you mix things together, when you change things, do you ever get a different number out? If I start with 10 grams, can I ever get anything other than 10 grams out? No. If I have 1 mole, can I get something different than 1 mole? 5 electrons? Has to be 5 electrons out, doesn't it? And so if I start with 4 orbitals, how many orbitals do I have to have out? 4. The exact same number, right? Never more, never less. Okay? And so if I have 3 p orbitals, 1 s orbital, they're going to mix together. They're going to make this right here, which is called the hybrid orbital. This specific one is going to be an sp3 orbital. Okay? The lobes would change a little if you had less p orbitals, in case you're curious. Notice that it has a bit of directionality to it in this case, doesn't it? Okay? And that has a large lobe and a small lobe, unlike the p orbital, which is equal. Okay, so if we mix these together, the energies, the s orbital was lower energy, right? That's why it got filled in first. The p orbitals were higher energy. That's why they were filled in second, later on the periodic table, right? And so what you're going to see here is when you hybridize those orbitals, they have to be the exact average in between. Okay? So it's literally going to be a weighted average of those energies, right? So the energy of 1 s orbital plus 3 p orbitals divided by 4. Okay? And that's the average right there. Those are your sp3 orbitals. All right. And so in our hybridization here, because see how it says sp3, that's telling you it has how many s orbitals? 1. How many p orbitals? 3. And so percent character-wise, that is, well, 1/4 s, 25%, right? 3/4 p, 75%. Okay? Okay, so again, the sp3 orbital is much more similar to a p orbital, obviously, than it is an s orbital. Okay, and you can actually see that out of these orbitals, right? It looks more like a p orbital. It just happens to have one lobe that's bigger, doesn't it? Okay, and so you can see that quite nicely, actually. Let's say that I had less p orbitals in this. What do you think happens to these? They're going to look a bit more like an s orbital each time, aren't they? Okay, and they're going to act more like an s orbital, right? So the more s orbital you have in it, the more like an s orbital it's going to be. Okay, the more p orbital you have in it, the more p orbital like it's going to be. Okay, that includes the energies will shift, won't they? Mm-hmm. We'll talk about it in just a second. Okay, but you can exclude p orbitals to make other things. It's if something else needs that p orbital. So energetically, it's more favorable to use that p orbital for something else. Okay. Okay, so this is what that looks like in terms of the sp3 orbitals right here. Okay, and that's how they all fit together. So they have the one large orbital. They each fit out in the prongs. That would be that tetrahedral shape, right? Notice it even looks like the balloon example we used to give you for Vesper and Gen Chem 1, right? Like it looks like a little balloon with a little tip right there, right? You tie them all together and get tetrahedral, right? So the balloon example actually works really good. Okay. So again, this is going to be where you get your sigma bonding. These are going to be direct overlaps. So you'll have an sp3 orbital from the carbon. This is going to directly overlap the s orbital in the hydrogen. Okay. Can hydrogen hybridize, by the way? Does it have any p orbitals to hybridize with? No, it doesn't. No. Okay, now when these orbitals overlap, they're going to create what's called molecular orbitals. Okay. I'm giving you the terminology now and the thought that they exist, but we're going to talk more about them in a bit. Okay. You've already played with them before in Gen Chem, where you made MOs from AOs, right? So AOs, atomic orbitals. You made MOs, which are molecular orbitals. Okay. Currently, we're still talking about atomic orbitals. We're not actually talking about molecular orbitals yet. We're indicating they exist, though, here, because overlapping, creating bond. Okay, so when we actually look at these, this is going to then build up our molecular orbital, right? In this case, we're looking at sigma molecular orbitals, okay? Or bonding molecular orbitals. Another way of saying this is sigma bonding molecular orbitals, okay? Them being direct overlap, bonding orbitals. When the electrons are put in these orbitals, what has to be true about those electrons? An orbital holds how many electrons again? 2. And can they be the same arrow direction? Same spin? No, they can't be same spin. Yeah, they have to be different spins, don't they? And that's what you're seeing here. They were same spin. They actually have to flip and have different spin. Okay? Okay. Okay, so the H and Cl atoms in HCl, they're going to be held together by a single covalent bond. Let's apply the VB valence bond theory to describe that bond. What type of symmetry does that bond have? So these are the things I want you to think about. Oops. You have to try your best to answer as best you can. It's okay if you don't get it, but you need to know where you fall apart. You got to test your understanding. All right, I'm going to go ahead and start forward since most people kind of set down their pens and such. All right. So one of the things we want to think about is the electron configuration of the individual atoms, right? So our valence orbitals, what do they look like? Okay, what valence orbitals are half filled? Because those valence orbitals are going to be the ones that will overlap, okay? And they're the ones that then pair those electrons, so then you get your bond. Okay, so if we're looking at hydrogen, then that's a 1s1, isn't it? Okay, first period, S block, 1 electron in it. If we look at chlorine, now, honestly speaking, I would normally just put the noble gas first. You can do bracket noble gas that you start with and then go to the next period, right? But if we go through, then we're going to see that we're 1s and then we're full, right? We're past that. And then we go to the second period and we're past that one, aren't we? So that's going to be 2s2, 2p6. Everybody okay with that so far? Did anybody fall apart when I started doing that? Okay. Then you're going to go, that is at that point isoelectronic to neon. So you could go represent the 1s2, 2s2, 2p6. You can just go neon, and that would represent that. Okay? Okay, so the next part is we're on the next period. That's going to be 3, right? So period 3, we start on the s orbital, and we're past that, aren't we? And chlorine's past that. And so we go, there are 2 electrons in that. And then the next one, we go to the P block, which is where the carbon, nitrogen, oxygen, fluorine, and all that is. Okay. And we go 3P. And then we go, how many were into that, right? Okay, so how many are we in on that one? 5, yeah. We're not quite full, are we? Okay. That's what Cl minus would be full. Okay, so that's the unpaired one right there. And so what we're looking at here is that one of these 3p orbitals has an unpaired electron. Okay, so we'd have 3 orbitals. They'd be the px, py, pz, and they'd be the 3 period ones, right? The valence shell ones. These are like so. So this orbital right here is the one that can make a bond. Okay, that one's the empty one. In this case, because we only have one thing and it's going to be stable as one thing by itself, it's linear, right? We don't have to do any hybridization. That doesn't make any sense to do that, okay? Because you don't gain energy either way when you hybridize. The reason it happens is because this finishing structure will be more stable. Like for the example of tetrahedral versus the other carbon structure, which would be much less energetically good, okay? Okay, so we get an overlap. We're going to have the hydrogen orbital. Can everybody see that okay? On the screen? Okay, so we're going to have the hydrogen 1s orbital overlap with 1 electron in it, right? And then we're going to have that 3p orbital that only had the 1 electron. That's going to overlap. And that's going to create the bonding orbital right here, okay? Now notice, because the electrons both are going to want to stay mostly contained between those two, you're going to get a buildup of that orbital area that basically wraps around the hydrogen chlorine, okay? And that's where that orbital is going to shift in terms of probability. Because what are orbitals? Where you find the electrons, right? That's all they ever were, okay? Now, what do you notice about this side, by the way? There's a part of that p orbital that is directly opposite of bonding, isn't it? Can you see that? Like, that does the exact opposite of bonding, doesn't it? Okay? Think of it like this. If you grab a hand with the person next to you and pull, then you're going to get bonding, right? You're pulling each other together. What if somebody grabs the other side and pulls you the other way? That's anti-bonding, isn't it? They're pulling you apart. Okay? Huh. When I add 2 orbitals together, how many orbitals should I get out? Same number, 2. I only talked about 1, didn't I? Oh my goodness, Dr. Clausen's going to see now. Still funny now. 10, 20 years, probably not going to be very funny. You know what they say, right? Chemistry professors continue teaching until they forget that they're teaching 3 times in a row. Okay. So this is going to be the beginning indicators of what is called anti-bonding orbitals, right? They're very high energy orbitals. They're going to cause bonds to get pulled apart. Okay? This is actually your first taste of anti-bonding right here. Right? You can see that we're starting to kind of make 2 orbitals, aren't we? Okay? Oh my goodness, you don't need me to teach you anything. You should just write these things all by yourself. Everything. Okay. All right, so this right here is again your overlapping orbitals, creating your bonds. Notice in this case here, what side of orbitals are we overlapping around the carbon? Do those look like p orbitals? Are they 90 degrees and there's only 3 of them? Those are 4. They're about 109 degrees apart, aren't they? So these are actually hybridized orbitals. These are sp3 orbitals here. Mm-hmm. Mm-hmm. Yeah, so it's linear. It has symmetry around this right here, as in like a barrel around it would be symmetric. But it's anti-symmetric this direction, isn't it? Can you see that okay? So this way it is not symmetric, is it? Because there's only 1 hydrogen on one side. Yeah. And so these are not symmetric right here. This axis here, though, is symmetric around it. So if you go around this as a barrel, that would be symmetric. Mm-hmm. Yeah, so if you look at the axis along the bond, it's symmetric around that. Okay. In terms of being perpendicular to the bond or the node here, that's going to be anti-symmetric. Typically, I would actually expect you to, it's not multiple choice. I would usually expect you to draw it out. Does it make your life easier? No, you draw this right here. If you're talking about the symmetry. So you draw something like this, and then you point out, well, it's symmetric around this part. But if you look at this part, it's not symmetric. And that's how you would easily do that. And that's actually pointing out, again, the bonding versus anti-bonding behavior. Okay. So this, again, is going to be your sigma direct overlaps. In this case, what we have is sp3 orbitals overlapping with hydrogen here. Notice the oxygen ends up as sp3 hybridized as well, because it's, again, an electron geometry that is tetrahedral. Okay? And that's what creates that tetrahedral electron geometry and allows for that, is the hybridization. Okay? So anytime you're tetrahedral geometry, guess what hybridization you are? sp3. It's the only way to get to that tetrahedral geometry. Okay, anybody have any questions about that so far? All right, notice again, whenever you make molecular orbitals that are bonding, they're always going to encapsulate the 2 atoms and be centered mostly in between them, right? And those are the bonding sigma orbitals, the direct overlap ones. Okay. This right here is actually lone pairs. Those are non-bonding electrons. Okay. Okay, so let's talk a bit about when you have double bonds. And this is where we're going to start introducing this other concept. That's going to be the other thing, where we reduce the number of p orbitals in that hybridization. Okay? Okay, so remember trigonal planar usually happened when you have double bonds? Yeah, made you do it a bunch of times in homework? Okay. Fully cognizant of it. Very good. Homework did its job. Or you did your job doing the homework. Okay, so trigonal planar is going to happen when you have sp2 hybridization. That's how you get that, is because you have three things all in three different directions, right? And they have to be planar because you have a p orbital that's going to be free. That is 90 degrees from those. Okay? Okay, so let's look at our structure. Again, we're going to be sp2 hybridized. That means how many orbitals do we get out from that? 3, right? Meaning 3 domains, right? 3 sigma bonds that are possible. Okay? Now, in terms of the character of these orbitals, we're going to be 1/3 s, 2/3 p, right? Okay. And right here, we actually see they're about 120 degrees. That gives us our triangle shape, which adds together to 360. And so these are both triangles around this, right? Okay, this is what this looks like in terms of hybridization for these orbitals. So when we're doing an sp2, we're taking an s, we're mixing it with 2 of the p's. And that's going to give us this set right here. Remember, they're going to all be in the same plane because we have no plane z. Okay, we never mixed any z in. Right? So they all have to be in the same plane. This would actually be referred to as an SPXY. So we're only the XY plane. Okay? We didn't mix in any of that upper plane, did we? And so that is why that's planar, is we literally didn't include anything from the other plane. Okay? It literally just does not have the other plane. Right? It's not perfectly flat, of course. It has thickness, but we didn't include any orbital that goes up and down. Okay? We just included one that's a triangle in one plane. Okay? And so that's the sp2. Everybody good with that so far? Again, why is it planar? Well, the remaining p orbital actually is occupying the space in that other plane, right? Okay. So altogether, this is what that looks like. These are our sp2 orbitals in our triangle. They're going to overlap and make bonds, sigma bonds. And then this right here is our remaining p orbital. In this case, we've oriented py to be up and down. Okay? And that is occupying that other space. Remember, this is a 90 degree though, okay? So from here to here is 90 degrees. Okay, does anybody have any questions so far? This is just the different directions. We're just flipping this each time. So we've included 2 p orbitals into the hybridization. This p orbital does not get included. No. It's not included. Yeah. So it's just still a p orbital. It never hybridized, and that's why it still looks like a p orbital, where it has the 2 lobes. So electrons are still there? Yes. Yeah. In this case, we actually have 1 electron. So there'd be 1 electron in it. It doesn't actually matter, though. Like, again, orbitals don't have to be occupied. Just like an empty room could still be over there, right? Doesn't matter. It could have electrons in it, could not. Doesn't actually matter. In this case, it's going to end up with electrons. Because we're going to do ethene. Okay, and so we have this. Now remember, ethene is going to be 2 sets of these, right? And so we're going to take one of these, and we're going to flip it around 90 degrees so they're pointing at each other, and we're going to bond them. Okay? And that's ethene right here. That has sp2 hybridization on both sides. See the sp2s right there. It has a free p orbital that's up on top. Both of those, in this case, have 1 electron occupying each of these p orbitals. Okay? Now, when you overlap these are sigma bonding orbitals, right? Everybody okay with that so far? So we have a sigma bonding right here. These are the carbon-hydrogen single bonds here. Okay? Okay. So that would be the single bond part of that carbon-carbon bond, right? Hey, look at this. We have these 2 other spots that are going to kind of overlap on the sides, aren't we? You can't see that? Huh. Shouldn't there be a double bond to this? I wonder how that double bond gets made, huh? Anybody want to posit a theory? Yeah, you're just going to get side-by-side overlap, aren't you? Okay. And that's going to give you your pi bond. That's a pi bond. That's the double and triple bond parts. Okay. And so what that is it's two free p orbitals that have not hybridized. They overlap side by side. And they create, just like this. Remember, this is the actual shape they are, especially if they're free and don't have any atoms on the other end. They're going to spread out more. Okay. And so they're going to overlap on their sides. And that's going to create, well, a p orbital, isn't it? Okay, so we have a pi orbital. Mm-hmm. Exactly. But I want you to move away from that terminology into direct overlap sigma. Okay? Is that making side by side overlap? Pi. Okay. But yes, if you still use the single bond terminology, sigmas. Okay. And so this right here represents a pi bond right there, where you actually have the orbitals mixed. Again, keep in mind that when we're talking about these orbitals, we added two orbitals together, and I'm just talking about the bonding version. Okay? There's also going to be another orbital that I haven't mentioned yet, right? Okay. And so this is the pi bonding orbital right here. Again, this would be a pi bond, and that's the double portion of a double bond. Okay. Anybody have any questions so far? It is not. It is still the same one. So in a pi bond, the bottom and top are both the exact same bond. And what you're kind of missing from here is you're thinking of electrons like a marker that I have to like go like this to go back and forth. Think of the marker just disappears from existence. And then all of a sudden it's over here. Okay. Think of it being super light. So light that if I touch it, it just goes launching. Okay. And so it's like you kind of have to remember that these aren't like normal matter. They're so light, so little energy that they can just like rocket up throughout space. These things are moving at fractions the speed of light all times. Okay, so that is one orbital right here. And it takes up the space above and below. You can think of it about like this. We actually have a node in this classroom. It's right there. See that? Everybody? So you guys are the two orbitals of this, actually. You know that, right? This is that pathway right here. And then we have our electrons, people, on both sides of the room, don't we? It's still one room, though. That's all that is. Yeah. So you never find any electrons sitting there. You find them on the two sides, right? Just like the classroom. Nobody ever sits there, do they? Yeah. That's that. Okay. Everybody okay with that so far? Yeah. Fantastic. Notice there again is a symmetry to this, but it's only ever symmetric in one plane. Can everybody see that okay? Because what it's built out of only is a single plane, isn't it? It's the two PYs, and they always have to match up. Okay? Mm-hmm. So we're above and below? Mm-hmm. Okay, so we're above and below. What if we move it in now? That space isn't occupied. Can you see that? Yeah. And so that would be a triple bond. Pointing out towards you, pointing away from you. And we'll see in just a second here. I have a figure of a triple bond. Yeah. So again, above and below, and now. All right. So this right here is a double bond represented with the singular orbitals. This one right here shows you those sigma and pi orbitals as their molecular orbitals. Okay? Okay. Okay, so let's talk about the next one. we have 1 sigma, 1 pi, that's a double bond, right? That's where the double bond terminology comes from. Literally 2 different bonds combined, okay? This is sp2 hybridized around these carbons, right? Okay. And so what happens if we take away another p orbital? Well, we'll get to that. But one of the things I want to remind you of, that we have 3 single bonds, no lone pairs, and so that would normally be a +1 formal charge. If we have this right here, this sp2 hybridization around a carbocation. So again, you'd have a free p orbital that's just empty in that case, okay? And it's going to be like so. This would be a carbocation. So again, you have sp2 hybridization, and then your p orbital is just empty. It's just not a bond because it doesn't have anything in it. Okay? Be aware of this because it will come up later when we start talking about reactions. It's incredibly important. Okay, now let's look at sp hybridization here. That was your question. Okay, so remember, in this case, we're going to have 2 p orbitals that don't get used, right? Okay, they're going to get used for something else. So again, 2 unhybridized orbitals will have an s orbital and a p orbital mixed together. And so our character for that single bonds, the sigma bonds, are going to be half s, half p. Okay? So they're going to be half s, half p, 50-50%. That's going to give us our linear geometry. This right here is the hybridization. So we'll have an s and a p. Those will come together. That's going to give us 2 orbitals here. And then what we're going to have is 2 free p orbitals. Now notice those p orbitals had directionality, right? And so one is going to be free and it'll be in the y direction, right? Up and down. The other one's going to be free and it's going to be coming out towards you. See that? It's coming out towards you and going away from you, okay? Because it's 3-dimensional space, right? So our sp hybridization is linear. It's only in one plane. See that? It's only in one direction. So let's say this is x here. This would be y and z, right? Now, this will help a little that by agreement through the chemistry field, z is always pointed towards the other atom. Okay? So this is actually going to be typically labeled z, and then this would be x and y. Okay? Okay, so let's see what that does when we actually do the hybridization here. So again, these are going to be the hybrid orbitals. They're the pz combined with an s, right? And they have directionality. Can everybody see that okay? The green ones? Okay. Or, I'm sorry, the X right here. That's the sp orbitals, the purple ones. Okay, now, these ones that don't have directionality, they're going to be our p orbitals that they don't have the hybridization at all. Okay? But they're going to be pointing out towards you and pointing up and down. And so when we overlap with something like that, what we're going to end up with is our sp orbitals are going to overlap in a sigma bond. And then our p orbitals are going to overlap above and below. And then the other p orbitals are going to overlap away and towards. Okay? And this is what they look like. So again, remember, we're in 3 dimensions. Okay? Take your hands, single bond. Above and below, that's 1 p orbital, right? Is your index ring finger. Go ahead and do it, everybody. Take your hands. Try it out. Okay, so that's 1 pi orbital, right? That is 1 double bond portion. Okay? If we have them the other way, that's the other pi orbital. Okay? And that's going to create the other one. Is that making sense? So remember, it's in 3 dimensions. Right? Okay, so again, that's the orange one right here. That's 1 pi bond. The yellow one is the other pi bond. Okay? And this all together is a triple bond. It's at 1 sigma, 2 pi bonds. Can you ever have more than 1 sigma in a grouping of bonds? No, you can't, right? because it's going to take the space up between, isn't it? So you can never have more than one sigma in a single set of bonds. Like a triple bond can never be more than one sigma. Because by definition, it takes up that space in between the direct overlap, right?
I guess you can never have more than 2 pi bonds.
No, you can't. And that's why there's no quadruple bond. Yeah. Now, technically, if we started including d orbitals, we might be able to get something similar to it. But it'd be very high energy. Okay, so go out in your PhD, and this is your chance to prove Dr. Clausen wrong. I'm going to make a quadruple bond, and then I'm going to write a paper, and I'm going to say that stupid organic professor and his stupid rule. Okay? We have a deal?
Right.
Okay. Somebody in this classroom, okay? You need to go out into chemistry, and you need to make the quadruple bond so that you can publish it, like put my name at the bottom and go, fucking Dr. Clausen is stupid not knowing a quadruple bond exists. Okay. No, I'm serious. You guys have no idea how often that, like, they don't usually say that person's name, but like, the rule that I was taught in organic chemistry was this. You can make a bond out of a single electron. You can do an overlap that's a different hybridization. You can do a carbon and have a double bond on this bridgehead. Yeah. I have no idea how often it is. It's actually kind of awesome because it like progresses science. But I challenge you all. Prove me wrong. Make the quadruple bond. Mm-hmm.
So like on that overlap, how are you getting some to like on the
What's up? This one? This, when it hybridizes, is going to redistribute. So that's this over here. Mm-hmm. Because these become much closer energy. Yeah. It's this. That's where these come from. Yeah. So S and P, right? The s orbital goes into the sp hybridization. Yeah. So that's why we have the exact same number of orbitals, 4 total. Is we have sp, they hybridize. They give us halfway in between in terms of energy. And then we have 2 free p orbitals here. They become much closer energy, so the electron goes ahead and jumps up to that next one instead of being paired, because pairing is higher energy as well. And then we get distributed. Exactly. We had 2 of the exact same set of 4 orbitals. We had the ones that overlap directly. We have the one that is above and below, right? And so they end up overlapping side to side, sharing 2 electrons. And then we have the other one that's towards and away. That make sense? And okay, full disclosure, like we do this and make this like really easy to sort of look at and try to trace the electrons. But if you did have an overlap of a p orbital and it didn't have the electrons already pulled out into that, it would do it. Like if these electrons can actually bounce back and forth. And literally you'll have electrons that this electron probably spends some time down here. Okay. But once they get close to each other and they collide, to have a reaction, it has to redistribute this way. If it didn't, it wouldn't react and it'd just keep colliding. Okay. That makes sense. Kind of like when you shake a hand, right? Like you go in, you're not quite the right shape, so you then shake the hand. So if you had 2 of these and they weren't the right arrangement, they'd repel each other and make themselves strike. That's part of that collision energy. Okay. So this right here is the Vesper theory. You guys didn't realize it, but Vesper was actually a reflection of what we've just learned, right? Like all the shapes require these sp3 hybridizations, sp2, sp. hybridizations, right? And so if we look at linear, then that's always going to end up being an sp hybridization, and that's because you have bond angles of 180 for your single bonds, right? Your sigma bonds. And that's the only way to get that 180 spread with two bonds. I do it. If you have trigonal planar, that's sp2. That was the number of electron groups, was literally counting the sigma bonds, wasn't it? So the number of electron domains, you were counting sigma bonds. The sigma bonds were spreading each other out, and that was what was the sp2 hybridizations were. Okay, that's how it got that spread out. And the bond angles are created by that sp2 hybridization. That's 120 degrees. sp3 tetrahedral, that's 4 sigma bonding groups, right? 4 electron domains, 4 electron groups, and that's 109.5 degree separation. Okay. And so, oh my goodness, we just completely rewrote why things happened from the stuff you learned, didn't we? Okay, so solve this. What is the hybridization of each non-hydrogen atom in this molecule? How many total sigma and pi bonds are there in these different bonding arrangements? I might end up taking my time a bit on this chapter and just dragging some of it over to next lecture, just so we make sure that we have the bases covered and you guys actually understand this stuff, rather than me pushing through. I think I already moved the homework back. Double check it though. If I haven't moved them back, send me an email so I can remember to do it after I finish my day. Because I have a long day. Usually. Okay, folks. I'm going to start moving forward here. Okay, so how do I figure out my hybridization? Well, I just need to look at my number of pi bonds in every case, don't I? Okay. Every time I have a pi bond, that means I had to have removed a p orbital, didn't I? So right here, I have a double bond on this one. Okay. The 19th is Friday, isn't it? Yeah. So yeah, I counted for that. Okay. And so right here, I have a pi bond this is involved in. That means this carbon has to have one p orbital not included in its hybridization, right? And so automatically that makes it sp2 because we have one p orbital that's been removed, right? Okay. This one also has to be sp2 because it also has to have one p orbital removed, doesn't it? Okay. This one here has nothing it's using a free p orbital for, and so what hybridization does it have to be? sp3. Yeah, they all have to have gotten used, didn't they? Okay. If we happen to have a carbocation here or a carbanion, well, carbanion actually would be sp3 as well, but a carbocation here, that would be something that you have nothing in a p orbital, right? Okay. This one right here, do we have anything using that p orbital other than sigma bonds? No. No. So sp3 again. This one also has to be sp3. Yeah. Because again, we have nothing that has to use up a p orbital not in hybridization, right? So they're going to hybridize. This one, sp3, this one. So we have one p orbital that has to be used up in this. The second one has to be used up there. And so we've used up 2. That's going to leave us with one only p orbital. So sp. This one. Okay, so same thing, doesn't it? Yeah. Because again, it has to contribute a p orbital into the double bond, p orbital into the triple bond, right? And that means it only has one p orbital. So sp. Okay, so how do I determine how many total sigma and pi bonds there are? I can, but probably the easiest way is just count up the number of bonding that's going to happen. Okay. And now the easiest way to actually do this is going to be to count up the number of bonds things want to make. Because remember, the hydrogens are not shown here, right? Okay. And so counting the bonds, you'd have to go, well, there's 2 hydrogens here, 1, 2, right? So if you count the number of bonds things want to make and then subtract off the pi bonds, your life will actually be easier. Okay? So if I count my number of carbons, there's 5 in here, and then a 6th one here, right? So each carbon, let's go ahead and count the 1 oxygen and 1 nitrogen, right? Carbons will make how many bonds? 4. Oxygen, 2. Nitrogen, 3. And so if we didn't have any pi bonding, this would be our number of sigma bonds, okay? Now, we have pi bonding, don't we? Okay. And so what we want to do here is we then have to sit here and figure out, well, okay, then what is our pi bonding contributing to this? Okay, and take that out. Okay, so let's think about this real quick, right? Right here, again, we have 4 that we need to make here, right? Okay, we have 3 that are accommodated for, and there's 1 more, right? So this is going to be 3 right here, right? Sigma bonds. Okay, and then this is going to be another 2 here, right? This one here is going to be another 3 that we haven't accounted for yet. Okay? Everybody seeing how I'm going through and measuring these? It's the number of bonds that they want to make. Yeah, I'm counting up my hydrogen by using the number of bonds. Yeah. Now, if you want, you could also sit down and just redraw this with the hydrogens. Okay? If you're nervous. One of the things you have to be careful for, though, is don't double count. Okay? It's very easy to double count. Right. If you're having trouble with what I just said, draw this out. Literally take your pencil and go, there's hydrogen here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1 hydrogen here, right? 9, 10, 11, 12, 13, 14, 15. Okay. And you can literally just count through them. All right. Okay. So again, right here, this is expressly written out. Again, here we have the hybridization. So linear, it has SP, SP3s there, SP2s there. Okay. This right here is going to be your number of sigma and number of pi bonds. You just go through and count out through the structure. I would highly recommend when you're doing this on an exam, and it's going to be important to get the points, that you go ahead and actually write small numbers next to each one so you don't double count. Okay? You're going to be nervous. You're not going to think, when you're nervous, you don't do as well as you normally would, most people. And so, actually label. Okay. All right. Does anybody have any questions? How many sigma bonds were there? That was the one I counted out. There were 13. Okay. How many pi bonds? Oh, I'm sorry. No, there's 15 total. Yeah. Yeah, I didn't count these ones, when we were doing it. Okay. How many pi bonds? 3. Yeah. Okay. Huh. I broke the thing. Okay. Now let's talk about bond rotations. When I have a double bond, can I rotate around it? That can allow me to rotate? No, not really, right? See, I can't actually rotate. Okay, what if I have a single bond? Can I rotate? Yeah, I can fully rotate, can I? You can actually prove this with your fingers as well. So if you're on an exam, you're trying to figure out, could I rotate around this? Is this free rotation? Double bond, can I rotate this without breaking that? No, the only way I can do it is by breaking it. If I have a single bond on the other hand, I can freely rotate any direction I want around that single bond without breaking it, right? Okay, and so that's referred to as free rotation. It can occur around single bonds. It can't do it around double bonds. It can't do it around triple bonds, but usually that isn't much of an issue around triple bonds. And it's again because of the presence of that pi bond. Remember, the pi bond is above and below. If we were to actually rotate them, it would no longer match up, and you'd no longer have a pi bond, right? You'd break it. Okay. Okay. Now, this right here, that means that they have to lie in the same plane. Okay? So if you have a pi bond, then all the bonds around it end up being locked in place in the same plane. Okay? And they can't ever not be in the same plane. Because if they're not in the same plane, you've broken the pi bond, haven't you? Okay? Okay, now keep in mind that if you have two pi bonds, they're both joined together, by definition, they then have to be opposite planes. Can you see that? They have to be perpendicular to each other. Okay? Because one pi bond set is above and below. The other one then has to be in and out, doesn't it? Kind of like a triple bond, but doesn't share them all in the same set of atoms. Okay? Okay. And so that right there, these all have to be on the same plane. Now, because there's no rotation around these, whenever you have a double bond, they can actually differ by a hypothetical 180-degree rotation. And this is going to be called having different configurations, okay, or different conformers. We'll talk about conformers in a bit, though. That's more of a next chapter thing. But, so what this is going to be is if you have groups on the same side, see these chlorines right here? Okay. They're on the same side, and so they are cis. And I want everybody to do this with me. It's a little silly, but it'll make you remember. Okay, ready for it? On the same side. On the same side. Everybody with me? On the same side, they are cis, right? Literally, cis means being same, right? Same side. Okay, so trans means on different sides, right? And so trans is where they're on different sides. Okay? All right. Everybody good with that so far? Okay. And so we have the trans configuration, different sides. Cis configuration, see same side. Okay. Don't trust me. You're going to get to the exam and you're going to be like, see same side. Oh, cis. There's going to be a bunch of you. Okay. You'll even hear it as like a murmur. All right. Does this molecule have two distinct configurations about the double bond? So if you did a 180 rotation, would that look different? Yeah, it'd look different, wouldn't it? If you swapped these, that'd definitely be different, wouldn't it? Okay. All right, so these would be the exchange right here, and you can see they're definitely different. In this case, you'd have the chlorine atoms that are on the same side, and so they would be cis to each other. This case, the chlorines would be on different sides, and they would be trans to each other. Keep in mind that we're referring to cis and trans. It's always going to be in perspective to something. Okay? So you always have to like say they are cis to each other in perspective to the chlorines. Okay? We'll have another terminology which we'll bring up in a fairly short amount of time that is actually has rules. So it's an always and E or Z. But this one is always needs to have context. Okay, context is very important. Let's talk about multiple double bonds. So some molecules can have more than one double bond. Each of the double bonds can potentially have different configurations. This is actually where you've heard of cis versus trans fats. Has anybody ever heard of that? Yeah. So That's cis or trans in reference to the double bonds. Okay. And so right here we have alpha linoleic acid. This has cis bonds right here. Can you see how they're cis in reference to the chain? Okay. And so all three of these are cis. Neat, huh? It's like this stuff actually matters and is used in your lives all over the place. Go figure. Okay, now modeling kits actually show the extended geometry is about the double bonds. They can actually be quite useful for this. They can also help you see the freedom of rotation around the sigma bonds. They can also help you show the restriction around the pi bonds. If you have modeling kits, go ahead and use them. It'll help you. However, if you don't have a modeling kit, then use your hands, okay? And objects in the world around you. You can actually accomplish essentially the same thing as I've been doing up here, right? I usually just go ahead and use my hands because then you guys know how to use your hands for this. And typically you don't have your modeling kits on exams. Okay. All right. Now, these are the extended geometries here. Remember when I was talking about the double bonds can't be the same side if it's 3 different carbons? Now we can see it pretty easy here, can't we? So this is a double bond above and below. This one's in and out. And they can never line up because they're share the same carbon here, don't they? That carbon's pure orbital in this direction's already used up. It can't use that one for the other double bond. So that other pi bond here can't use the pure orbital in this direction, can it? Okay. And that means it has to use it in this direction. Then now. Not making sense? Okay, so as the hybridization of an atom goes from an sp3 to an sp2 to an sp, the bonds are going to become shorter and stronger. So what we're going to see here is they're going to be more and more S character, right? Where do those electrons typically lie in terms of S character? Closer, don't they? And so as you get more and more S character, you're pulling that more and more towards the nucleus, okay? The other thing that's happening is, remember, S orbitals are lower energy, right? So if I average something that's a real low energy with 3 things that are higher energy, what happens to the energy? It goes up. If I average it with 2 things instead, it goes up less, doesn't it? 1 thing goes up even less. Okay? And so that means these energies are very, very low energy, very stable when we're talking about an sp hybridization. When we're talking about an sp2, they're going to be higher energy. sp3, higher energy. That means they're less stable. They're going to take less energy to break if they're less stable. Okay? Yes. Yes. Your sp orbitals are typically going to be quite a bit more stable. All other things being equal, if you have completely different atoms, then this isn't going to matter. But carbons. Okay, and you're actually seeing it right here. So notice that this right here is the sigma, then we have a sigma pi, and then we have 2 pi's here, right? And so what's happening is the only thing that's changing on these carbon-hydrogen bonds that are next to it is the hybridization. That's it, okay? This one's an sp3, sp2, sp. And we can actually see this change. It's not a big one, it's pretty small. But this is 108 picometer, 107, 105. See how it's shortening? Okay. And this one here, the energy, it takes 421 kilojoules per mole to break this. That's 464, and then 558. It's a noticeable difference, but again, keep in mind, if you're talking completely different atoms, this is not that big of a difference. Okay? So, carbon-carbon, though, it's a significant bit difference. By the way, interesting little factoid here. This also affects a lot of other properties. For example, this hydrogen is much more acidic than these ones. No. Ooh, you didn't know that, didn't you? We'll talk about that in a bit, but it actually affects a lot of properties. Like this is extremely meaningful and reactions are happening all the time in your body right now because of this. Okay? So, The S character of your hybrid orbitals, again, increases as you go from sp3, sp2, to sp. This is actually what those orbitals look like. So here we have p orbitals, just purely p orbitals. Okay. As you increase the S character, this is how they're going to change. So right here we have an sp3. It's mostly like a p orbital, right? Okay. And you can see it juts out a bit more here. And it actually has less lobing. See that? Where the lobes are actually more symmetric. Okay. As we take a p orbital away, see we get a little less symmetric, don't we? It's more asymmetric. This actually gets pulled in just a little. Okay. And then we get to sp here, and it gets really asymmetric, right? Because our lobe here, this is more like moving this up here. And then our lobe gets shrunk down. Okay. And you can see that actually gets pulled in even more because it wants to be closer to the nucleus. Okay. So the hybridization of an atom, as it goes from sp3 to sp2 to sp, the effective electron negativity increases. And so right here we have ethane, and we can see that the charge difference isn't hugely different, right? And that has to do with the concentration of electrons. So what we're going to see here, as we go to sp2, look, notice what happens to our hydrogens. They get more positive, don't they? And this gets a little bit more negative. And then we go to sp hybridization, our triple bond, and all of a sudden our hydrogens are actually pretty positive, aren't they? At the end here. And we have a lot of that negative charge that gets concentrated in that triple bond area. Okay? Ooh, we're getting acidic, aren't we? That's where the acidity comes from. Is we're starting to pull electron density away from the hydrogens. And we get more stable with the electron density here. Okay? More contained away. Okay. So in which molecule, A or B, do you think a C-C double bond distance are longer? And which molecules are the C-C bonds stronger? Remember, it's the hybridization you need to think about. So don't forget, you can do problems on your homework without doing all of them. You can skip to other problems. So do the ones that we've covered, make sure they're done and ready to go. And the ones we haven't covered, you can kind of set yourself up and make sure you understand which ones they are and how you what you do know about them. Then come in. Okay. I'm not gonna force myself to finish this in this period because I think it'll do you less good than just leaving a little bit. Okay, let's go ahead and go on. Okay, so what's the hybridizations again? Yeah, we're going to be sp2 hybridizations, right? Okay. Okay, very good. And so we're going to end up with sp hybridizations, sp2 here, sp2 here. These are all sp2 hybridizations, right? This one is a what hybridization? sp2, right? Okay, three different things. This one is sp2. How about that one? That's just sp, isn't it? Yeah, two of the p orbitals are used up, aren't they? So we can only do an sp. Okay, and so this one right here actually has a 50% s character when we're talking about these sp orbitals, right? They're going to end up being used in those sigma bonds, right? And so in terms of bond length, you would expect those to be shorter, wouldn't you? Okay, how about the energy? Well, it's going to be a lot more energy to break them, right? Not a huge amount, but it's going to be more energy. Is that making sense so far? Okay. I know we added a bunch to your understanding, didn't we? There's a lot of consequences to that. You'll actually not understand every single thing I've taught you this entire year within the year. That's why you need a whole nother class called biochemistry. Yeah. Okay, so let's talk about the wave-particle duality. Electrons have characteristics of both particles and waves. That's actually what we were talking about when we were talking about this before. Why that doesn't make sense that they're split? Because they're actually wave-like. waves have nodes. And so when you look at a wave, so this is a probability wave. This right here is 0 and is a node. Okay? And so that actually means they have nodes, and they pass between those nodes without actually going between. Okay. And so an electron, these can be described with a wave function. This is phi here. It says a numerical value. It's called an amplitude at each point in space. The amplitude of an electron's wave function is going to be analogous to the displacement of a rope when a wave is generated along the rope. And so has anybody ever done this, where you take ropes and go like that, or seen that done? Probably when you're a kid with jump ropes, would be my guess. And you see the wave travel along the rope, right? But the rest of the rope is mostly flat, isn't it? And actually, it gets disturbed incredibly little, like considering what you're doing, right? And so this is very similar to how waves work in any wave function, whether it's an electron or not. In this case, we're talking about a wave function for electron. Does everybody remember where they were seeing like these math terms pop up when they talked about orbitals back in Gen Chem? And you didn't really actually talk about them. They were just like in your book, and then everybody just ignored them. Okay. That was actually wave functions. And those wave functions are what are added together to build these orbitals. Okay? And so they're what actually make the orbital. And when you're talking about an orbital, you're talking about a 90% chance of finding them. That 90% chance of finding them is the wave functions. Okay? If you want to go like far in depth on this, that would actually be PChem 2, if you ever want to. Okay, so now, when we're talking about waves, they have phases, right? So just as a rope can be displaced in either direction from rest, an electron's amplitude can be positive or negative, and this is going to be the electron's phase. It'll be positive and negative. Okay, you've already seen a little bit of this because we have positive and negative spins, don't we? Okay, and those were phases for electrons. That was one type of phase for electrons. This would be the phases of rope, by the way. And so if you had two people, they both send a wave through the rope, and their phases, their amplitudes match, but opposite, their opposite phase, amplitude matches, what happens to them? Cancel, right? You don't see it anymore. You can see this in bathtubs too. You've probably played with that before. Like you bounce waves around, and then you do like a different beat, and it cancels them all. And then the tub becomes kind of flat. Okay. You're playing with that when you're doing that. You're doing the opposite phase, and so they're canceling out. It's called destructive interference. If you do it where you add to it, you know how you do a jump rope where you do like this and you get the right beat to it, and it makes it louder and louder? Yeah. That's going to be the same phase. So you're matching phases, constructive interference. Okay? Okay. I am past time. We'll start up on here next time. You all have a wonderful day. This is, by the way, quantum mechanics. We're going to just touch on this enough that you kind of understand bits and pieces so you can understand orbitals to some degree.